everyone. As Dr. Wong said, my name is Prachi Chapman, and I am the current chair of the Chemical Engineering Alumni Committee. And it is my honor tonight to present tonight's speaker, Dr. Matteo Pasquali. Dr. Pasquali is the A.J. Hartsook Professor of Chemical Engineering, as well as Chemistry, Material Science, and Nanoengineering. Since joining Rice faculty in 2000, he has served in various capacities, including the chair of the Department of Chemistry, former master of Lubbock College, chief scientific advisor at Shell. He's also been the director of 2 startups that he has co-founded. He's an elected fellow of the American Association for the Advancement of Science and the American Physical Society. He has won numerous awards over his career, including the NSF Career Award, the Garadia Innovation Grand Prize, and the Rice Presidential Mentoring Award, just to name a few. Dr. Pasquali has also advised over 90 grad students and postdocs, many of whom have gone on to key positions in leading universities, industry, national labs, and startups. He received his PhD from the University of Minnesota and a Master of Science from the University of Bologna, both in chemical engineering. On top of all of this, Dr. Pasquali is the current director of the Carbon Hub here at Rice University, which will be the focus of tonight's lecture. So without further ado, I am excited to present Dr. Pasquali.
Well, thank you, Prati. Thanks to all of you, and thanks to Chevron for sponsoring the lecture. I'm very honored and humbled to be asked to speak. First of all, it's unusual to be asked by your own institution to speak, although COVID made it a little easier, I think. And also, this lecture has been given by many distinguished colleagues. The first one was actually Lenore, who happens to be one of my academic brothers by way of Skip Scriven, and then George gave this lecture a few years ago, and I'm very close to George. I inherited his endowed chair. George is the Hartsook Professor Emeritus, and he's been one of my mentors since I've been on the faculty. So I tried to start with a provocative title, you'll see that the hydrogen doesn't have any color, it's free, and I'm going to argue that we can use carbon to decarbonize. So what do I mean? So these days, a lot of talks start with this graph. So how the carbon dioxide concentration has evolved in the atmosphere over the last few 100,000 years, okay? And then what you see is right about at the time where we figure out how to convert heat in mechanical energy, the Industrial Revolution starts. We discover the law of thermodynamics, but not all the implications, and the CO2 levels go up, right? And then usually there is an accompanying chart that shows that the temperature on the Earth goes up. And so the speaker will show this graph, and then he will argue that we must decarbonize. Okay, so I'm not disputing anything about this chart. I'm not disputing that the temperatures are going up, but I'm asking, do we really have to decarbonize? So the first thing is we are carbon-based life form. You know, most of us took biology before we took thermodynamics in high school, and we were told that we're carbon-based life forms. If you exclude water, which is pretty much in here just to fill the voids, because we're big porous media, 50%, over 50% of our body dry mass is carbon. More than 50% of our food is carbon. More than 50% of our clothes are carbon. So we can't really decarbonize. Carbon is actually not bad. If you don't believe me, it's even on t-shirts, okay? We're a carbon-based life form. So the problem is not carbon, it's carbon dioxide. When we burn carbon, combine it with oxygen, and that's really what that graph is. It's not talking about carbon, it's talking about carbon dioxide. So interestingly, we have a language challenge. We don't have a trade word for carbon dioxide. And I speak Italian and a little bit of a few other Western languages, Western European languages. There's no word for carbon dioxide in Spanish, in French, not even in German. There's Kohlensäure, which is the acid that comes from coal, but it's really not carbon dioxide either. And I've asked friends who speak other languages, like Asian languages, there doesn't seem to be one. It's very weird. We got a word for ammonia, we got a word for methane, much less important molecules. We don't have a word for carbon dioxide. Now this is not that big of a problem here because most of us have engineering degrees and we remember enough engineering to know the difference between carbon and carbon dioxide, but the people who make decisions and the people who vote for the people who make decisions don't necessarily understand that difference. And so what has happened now is we're saying that we must decarbonize, we need to stop using oil and gas, and we stop using hydrocarbons, when we really should say that we need to stop burning carbon. So I'm trying to use a new word. I'm trying to use decox. I know with my accent it may sound weird, but think about detox, right? It's we are addicted to burning carbon. And so, and it's COX is carbon oxide. Yes, it turns out that the bills in Congress don't talk about removing carbon dioxide, they talk about removing carbon oxide. So one thing we could try is maybe we could make a concerted effort to use a different word for carbon dioxide and removal of carbon dioxide than carbon. Now, why did we get into this problem? So there is a large carbon cycle, right? So right now we're all breathing out carbon dioxide, and there's lots of natural processes that emit carbon dioxide, but there are also fixation of carbon dioxide by plants via photosynthesis, and these two cycles have been in balance for a long time. Those fluctuations up and down in the graph below were actually periods where there were some natural imbalances that got corrected over longer time scales. And it turns out that the imbalance that we are generating in the carbon cycle is only about 5% of the total. And some people will say, well, so why is it that we're getting this problem? Well, the problem is, think about this as if you start eating 5% more calories every day, doesn't seem like it's a big deal, but then over time you're going to put up weight. And then at some point you'll get to a different weight where your metabolic consumption is higher and you stop. But the point here is that if we can promote some of the natural ways to fix carbon dioxide, we could actually do quite well. Now, the second thing to think about is that most of the carbon dioxide comes from industry. This is, normally we see this curve or graph that has electricity and heat as its own thing, but the electricity and heat is not an end, it's just a means to an end. And a lot of that electricity and heat is going into industry. Right now, very little is going to transport because we're mostly driving internal combustion engine cars. And so it has to do with industry. And what is it used for? Well, if you look at who's emitting, you see that at some point around 2000, the emission of China's go up massively, and the emissions of the European Union and the US are going down. Why? Because we started slowing down the rate that we're making stuff, and China started making stuff for us. So nature can help us, and making stuff causes CO2 emissions, okay? So that's an important message here. Now, one approach to deal with this is what's called CCS, carbon capture and sequestration. It should really be carbon dioxide capture and storage or sequestration. Sometimes it's also called carbon management. Why is it called carbon management? Because in this view, you essentially treat carbon dioxide as a pollutant or a waste, which is what has become to be. And so there's of course, there's a lot of efforts on how do you collect these carbon dioxide effectively and store it away. But there are two fundamental issues with this approach. One is, if it's a waste management problem, you got to pay somebody to remove it, and you have to pay somebody to store it, which is exactly the problem we have with waste management. We get a tax bill or an invoice for waste management. The waste guys don't pay us to take the trash away. We have to pay them. And then we got these problems with landfill. So inherently, it is something that you do because you have to do. And but making better trucks is not going to solve the problem of the fact you have to pay somebody to remove waste, and you have to figure out a way to put it away. Now, how big is this? If we look at urban waste, and most of you are familiar with the fact that, for example, there's difficulty in finding landfills, total urban waste is 2 billion tons a year. Total CO2 emission, 37 billion tons a year. Of course, they're gas. So this is a big problem. And what's interesting is right now there's efforts to get higher tax credits for CO2 removal. So right now, there's proposals to initially to increase the value of CO2 removal to $100 per ton. Now, at $100 per ton, removing 37, I understand nobody's going to remove the whole CO2 we emit every year, but if you could, you would have a $3.7 trillion business. Now, I did a postdoc in physics, and also I did my degrees in chemical engineering, and whether you want to call it dimensional analysis or scaling, it's the same thing. What does it mean, dimensionless? If you do $3.7 trillion a year, and you divide by the total revenues of oil and gas companies, it's 60% of that. Oil and gas is about $6 trillion a year. If you look at the world GDP, that's 5% of the world GDP. Okay, so that's how big these. Now, if you look at it a little bit differently, and you say, what about if I look at locally? So how much does a ton of methane cost? Now, I do realize that nobody talks about a ton of methane. They talk about the billion or gazillion of BTUs, etc. But it is actually healthy to use mass and energy in SI. So if you take a ton of methane, in Texas is about $150. Right now the prices are a little bit higher because of all the crazy stuff that's happening, but if you look at long term, it's $120 to $150. You send it to a power plant, you make electricity, and you make 2.75 tons of CO2, because CO2 is 70% oxygen. The oxygen is bigger. I don't know why it's always drawn with the bigger carbon than the oxygens, but oxygens are larger, they're more massive atoms, maybe they're. And so you would be paid $275 to remove it. Okay, so economically, there would be twice as much incentive at removing the CO2 than the value you get from actually extracting the gas and taking it to the power plant to do something positive. So this is something that has to be done, but we need to do something else. And can we do anything better? Can we do anything more? And so there is a way to try to do something better and more, which is look at 5 problems. They seem unrelated, but they're actually interconnected. One is clean energy sources. Of course, we're deploying solar and wind as fast as we can. We got hydro. We may go back to using more nuclear, but that's not enough. And hydrogen is an attractive form of energy that doesn't cause CO2 emissions. But where do we get it from? We can't go to the sun to get hydrogen. And on Earth, most of the hydrogen is either tied to water, which means that it's devoid of any energy, or otherwise it's tied to carbon. We need to decarbonize the industrial sector. This is what's called hard to decarbonize problems. That's essentially what I was saying about talking about making stuff. Okay, there is a lot of CO2 that goes into making steel, aluminum, cement, etc. Now, we want to lightweight transportation systems. We shouldn't forget that one of the best ways to reduce CO2 emissions is to become more energy efficient. So we use less energy. And so if we could make our aircrafts and our cars and our trucks lighter, that would be helpful. However, it turns out that if you switch from using steel to using aluminum or carbon fibers, you actually use materials with higher CO2 footprint. And so, you see, you're trying to do something better and something else gets worse. We want to electrify. So we want to electrify transportation systems. What that means is the cars are becoming heavier. A Tesla is about a good 30% heavier than an equivalent car with an internal combustion engine. And also, we need a lot more copper and aluminum. And an internal combustion engine car has about 30 kilos of copper. An electric car is about 90 kilos of copper. Okay? So there's a lot of pressure on those resources and associated CO2 emissions. The last thing is the economic impact of oil and gas. Now, this is one of the few times that the audience probably agrees with me because it's sponsored by Chevron. But there's places like Houston and Texas and the U.S. And companies like Chevron, but others too, that actually make a good living. And any of us who has a house in Houston wants that house to preserve the value. We don't want to become Detroit, right? And so this is about 8% of the global economy. And so if we stop using oil and gas, then we're going to have a lot of stranded resources and we're going to have a lot of economic turmoil. So can we actually use oil and gas to address some of these problems? Now, how do we use oil and gas now? So in metric tons, it's about 4.2 billion tons of oil and 2.5 billion tons of gas. I know it would be gazillions of TOEs or whatever, but in metric it's actually very simple. So oil is a little less than twice the gas. Now, from well to here, there's almost no CO2 emissions, especially if you're careful at not having leaks of methane and if you use renewables. For example, the operation in Norway have extremely low CO2 footprint for getting oil and gas out of the wells and into the transportation system. So there's almost no CO2 emissions up to here. The problem is at some point we add oxygen and we get these very large CO2 emissions. It's about 2/3 of the total, 19 out of 37 gigatons. Now there is a little stream over here, which is actually polymers and chemicals. And it's not that much. It's about 5-6% of the total. It's a very precious one. To those who tell me that synthetic hydrocarbons are bad, what I say, COVID was not synthetic. I think has been proven. And look at what it did to us. And the vaccines were synthetic. And all the masks that some of you are wearing and protected us, those were all synthetic plastics. So it is actually, materials are very useful. They're so useful and so inexpensive that now, unfortunately, we throw them away and we end up with waste problems. So can we reinforce that? And specifically, also so if we start taking oil and gas out of the energy system because we put it in the material system, we have another problem, which is we need energy. And if you look at this graph, it's been about the same for the last 20 years. About 75-80% of the energy is coming from hydrocarbons, including coal. So is there a way to preserve some of that? Well, this is, oil and gas is mostly carbon, right? There's a lot more carbon, even in methane, it's recorded carbon. But interestingly, if for a moment you forget about the enthalpy of formation of the hydrocarbons from the hydrogen and the hydrogen has half of the energy, okay? And so if we could use all the carbon for materials and all the hydrogen for energy, and I do understand we need to give it a little bit of energy to do that splitting, we will still have about half of that energy. So is it possible to do this? I'll do the example for splitting of hydrocarbons. This is stuff that has been done for over 100 years. It's in patents from before World War I. It actually was a prevalent method for making carbon black. You can take methane, natural gas, it's a carbon and 4 hydrogen, and if you put energy in it, you can split it, and you need 18.8 gigajoules if you want to make a ton of hydrogen, and you're going to make 3 tons of carbon. Okay? Now, this is very attractive from a hydrogen point of view because the hydrogen has a lot more energy than that. It's got 142 gigajoules. So you need less energy to do the splitting in the ideal process than the energy of the hydrogen. And then you get all this carbon. So you could say, I make the hydrogen, I get the carbon for free. Not really. There's only one color of hydrogen. Hydrogen is a commodity. There's no difference between the hydrogen coming from these processes or coming from electrolysis. Carbon is a specialty. And so when you do this process, different processes or the same process run in different conditions is going to make all different types of carbon. And so we have to pay attention to the carbon for 2 reasons. It's a majority of the mass and it's going to be a specialty. It's a material, it has to be placed differently. We need to figure out how efficient and how expensive this is. What kind of policies can enhance these pathways? And we got to realize that we have a complete mismatch on the markets. The markets for solid carbon are non-combustible solid carbon are very small. I had 5.5 gigatons in the previous slide between oil and gas, and here I got 10 megatons. Okay, so almost 3 orders of magnitude difference. Most of it is carbon black. There are some like carbon fibers that are great, but they remain very small because the processes for making them are extremely energy intensive. That's another thing. It's always better to measure cost in energy than in dollars. There's a lot of games you can play with dollars. You don't have a second law of thermodynamics or a first law of thermodynamics for dollars, but you do have it for joules. And so these are not just expensive in dollars, they're really expensive in terms of the energy needed to make carbon fibers. So how do we use materials? Okay, so here we have a palette of materials. You see carbon black, I put it right there. What you see is all the materials are on the top part of this graph are materials of structural integrity. Now over here, of course, some of them are natural materials. We don't want to go after those like construction wood because those are great sinks of carbon that's fixed via photosynthesis. Over here, we have concrete, asphalt, cement, glass brick. These are low-value materials, and they're used almost exclusively in static structures. It's going to be hard to displace, not impossible, but hard to displace these materials, starting with hydrocarbons that are more expensive than that. But there's an opportunity over here. If you look at metals, steel, for example, it's right now it's about 1.7 billion tons a year, and it's used in transportation, and it's higher value. It's anywhere from 80 cents a kilo and up. Using transportation, that means that density is a liability. High density is a liability. Also, these are the big offenders for the industrial CO2 emissions. Steel and cement are the biggest ones because their mass that we make are so large, but aluminum and copper are actually even worse in terms of intensity of emissions. There is one thing that we shouldn't forget, is that the CO2 problem is just one of many environmental problems that humans have been causing as they become better and better at controlling technology. 50 years ago, we were having a problem with other types of pollution, for example, mining. There's almost no mining in the US. Yeah? It got pushed out somewhere else, not because we ran out of ore, but because mining is a devastating environmental impact and activity. So right now, to get more aluminum, forest in the Amazon is being clear cut, rivers are being dammed to make electricity in situ and to make aluminum. And the impact of those activities far exceeds the CO2 footprint of making that aluminum. So we need to be careful as we try to solve the CO2 problem, not to take some other problems and make them worse, just because we don't see them, because this is happening in the Amazon and not in Texas, or it's happening in the center of Africa and not in California, right? So, for example, I think Chevron operates Perdido, right? I think Shell is the prime and Chevron is. So this is one of the largest oil platform in the Gulf. It's Perdido. And that's the largest copper mine in the world. It's called Escondida, which means hidden, and it's conveniently placed in the desert of Chile. That's a Google map image. I tried to find Perdido in Google Maps, and I couldn't find it. And the reason is, well, first of all, is that you don't have high resolution maps in the middle of the ocean. But the other reason is that this is not a big structure. Now, it takes out of the ground about 5 times more material than the whole site of this copper mine. But if you put it on the same scale, it's about as big as a truck shop of a copper mine. So Perdido is about half the size of a football field. It's about 50 by 50 meters. So the environmental impact on mining hydrocarbons is it's bad in absolute terms, but if you do the rescaling that physicists should do and engineers do against mining for anything else, it's about the best kind of mining we can do, okay? Maybe I should do a quiz. one of the US cities is built on an operating oil field. Which one? LA. LA is still on an operating oil field, the La Brea tar sands, right? And so you could never have a US city on top of a copper or aluminum mine. And actually that's another thing. So this is not getting better. Right now copper is mined at 0.3% concentration. So if you want a ton, if you want a kilo copper, 3 kilos of copper, you need to move a ton of ore, and it's getting worse and worse because the mines, it's not like we're running out of copper, it's getting harder and harder to extract. So what about if we were to get rid of metals? Well, we would save 12% of the world energy use. We may use some of that energy to make these new materials, but that's a lot. We would eliminate 16% of world CO2 emissions if we can take down also cement with it. And so Gates has this interesting question. He says, what's your plan for steel? And his plan for steel is always make steel in a slightly different way, which is what we used to do with power plants. Remember? You know, we basically started cleaning up our power plants, but we're still using coal. We're still using natural gas. And that's also what we did with cars, with internal combustion engines. We made them more efficient. Then at some point we tried to use biofuels. But then eventually, what are we doing now? We're getting rid of the power plant, the thermoelectric power plants, and replacing with solar and wind. We're already getting rid of internal combustion engines, replacing with electric cars. And so the plan for steel is replace it. Okay, so this is something that it's a type of future that people are not really looking at yet. Okay, it's but if you can do it, if you can replace steel with carbon, and you do this right, you can lower energy use and eliminate CO2 emissions at the same time. Now, so you know, putting all the story together is you start with something like methane, but you could do it with any other hydrocarbon. Split them. Now this is on the basis of a kilo of methane, so you need at least 4.7 megajoules, but you have then hydrogen energy. Now you're making something useful, and so you don't have to make it for zero energy. If you're displacing steel, if you can make that splitting at a lower energy than what you need for steel making, you're still ahead, and you haven't made any CO2. Now, you need some scalable processing to go from these materials, which have some samples over here. So this is what it looks like, into something that would have shapes that actually have structural integrity. And then once you have shape and structural integrity, you need to get properties, and then you go after applications. And you could use also other pathways. For example, some of you who do gardening may use biochar. Now, biochar doesn't have structural integrity, so why don't we use more biochar? Because it's too expensive. It's fine for gardening, it's not fine for large-scale use. And so if you could have pathways, for example, to make synthetic carbon efficiently, to use a soil amendment, you could also have a way to win and reduce the use of fertilizer. And so some of my colleagues here at Rice, Carrie Mazziello, Dan Cohen, Pedro Alvarez, in earth science and in civil and environmental engineering, are working on, they're trying to understand what are the characteristics of synthetic carbon that can make synthetic carbon displace biochar. And so these would have to be grades of synthetic carbon that are made at very high efficiency, primarily for the value of the hydrogen. But if they can displace biochar, they could actually increase fertilizer retention, so lower fertilizer use, and enable farming in areas that right now are marginal. Now, there's a company that's already doing this. It's called Monolith. Now Monolith is doing for carbon black. So they basically took the old ways of making carbon black by thermal pyrolysis, and they changed it using plasma, so you can use electricity very efficiently. And they realized along the way that they were making hydrogen, and so the Biden administration was going to be very happy with this. Now, this is not a small idea. This is a plant that is already making in the order of about 15,000 tons a year of carbon black. And this company just got a guarantee loan from the Biden administration last December. It's $1 billion loan to build a larger plant. And the larger plant, which is just built by duplicating the current plant, which is this one over here, this larger plant will be making about 0.18 million tons a year of carbon black, which is 1.5% of the world carbon market. And it will co-produce hydrogen that's going to be used to make ammonia for fertilizer. So between the carbon black that will be made in a way that doesn't have CO2 emissions and the hydrogen is used for fertilizer, it will displace about 1 million tons a year of CO2 emissions. But this is by doing a productive economic activity. They're selling this carbon black at a premium compared to the carbon black that's made by partial combustion of oil and gas. The problem here is, as I said, is these guys can only grow to 10, 12, 15 million tons a year, and then they got to find some other products. And so here is where I go to nanotubes, because of course I've already showed you it's possible to get a structural integrity if you use nanotubes. Now, nanotubes have an interesting story. They were discovered in 1901 by Ejima. Rick Smalley was actually looking for them here at Rice, but he didn't find them first. He found the buckyball, the spherical one. But Ejima found the nanotubes. And pretty quickly, it became understood that this was not a material, it was a material class, a little bit like polymers. It's a class of materials. And there was a huge amount of hype in the late 90s because of possibly deliberate, probably not, confusion between the properties of the molecules and properties of continuum. So if you take a single nanotube and you measure its strength, its electrical conductivity and thermal conductivity, they're very, very high. Now, of course, strength, electrical, and thermal conductivities are continuum properties that were defined during the golden age of physics during the period of continuous field theories in the mid to late 1800s, where they didn't even believe that they had atoms and molecules. So if you take continuum properties you apply it to molecules, you're going to be in for some bad surprises. So there was a lot of hype, and then Rick Smalley was probably the first one who figured out how to make macroscopic samples. And then there was very slow application development. And there was really very little control on how to go from powders to macroscopic structures. And the few times that this was happening, it could be done, the properties were terrible. Nothing close to the properties of the molecules. And so there was a big disillusionment. I remember in 2000, I was having breakfast and Scientific American published this article saying that super strong materials in carbon nanotubes were science fiction. Fortunately, that same day, George Irazaki had put a very exciting paper from Science under my door that showed that Philippe Poulain in France had made the first fiber of carbon nanotubes. And so I started working on this. So where are we now? Okay, now we're in a totally different space. And so what I'm saying is I'm talking about things that are already happening. There's this quote that the future is already here, it's just not very evenly distributed. So today you get to see the future the way I see it. There's companies that can make macroscopic materials with really good properties that rival the best metals, the best carbon fibers. There's companies that can now produce at hundreds of tons a year. For example, there's Oxial. I have a picture of the reactor of Oxial. You see the size of the reactor because there is a ladder. There is a ladder over here. So this reactor is spread about 4 meters in diameter. Huntsman, which is a company here in the Woodlands, is building a pilot plant right now at 18 tons per day. They've announced demo plants and then commercial plants to orders of magnitude scale larger. I have to say I have a conflict of interest. I co-founded a company called Dexmat. Some of the samples are here. So don't go out and invest in Dexmat after you hear this talk. Anyway, you couldn't because it's not publicly traded, but still. This is no longer a lab curiosity, okay? It's in the numbers over here, I'm not showing any type of nanotubes. Remember, I said it's a class of materials. These are fiber-grade nanotubes. You can make materials with structural integrity. What about properties? Well, as I said, early 2000s, nobody could make materials. And then some of us started putting dots on a property map. So these are the first fibers. Back then, you could get a paper in Science with 100 megapascal because it was nanotubes. 100 megapascal, it's pretty bad, okay? It's not a fiber to be proud of, but we could make a fiber, right? But then look at what happens with funding and persistent improvement. Every 3 years we double properties. And when I say we, it's not just my group, it's also other groups around the world. And it's true for tensile strength and for electrical conductivity. So over here, now, you're really at values of properties that start rivaling some of the best materials. Production was scaled, so and also forms and form factors became different, not just fibers, but braids, yarns, mats. This is a non-woven, and over there we have some woven samples. So the field really expanded. And in terms of properties, we're now in a situation where these materials are essentially as strong as carbon fibers and are essentially as conductive as metals. Especially if you do it by unit mass, you see that there's very little difference between carbon nanotube fibers and carbon fibers and carbon nanotube fibers and copper for electrical conductivity. Thermal conductivity is even better. So what has to be done next? Well, the next thing is cost reduction. And this one is a little bit different. This is not published, okay? I've shown it before, but it's not published. On the left, what we have is the cost reduction of solar. It's by a book called How Solar Power Became Cheap by Nabata, Wisconsin. So it turns out commercial solar went into satellites in the 50s for spying satellites. And it was about $400,000 per megawatt hour. Okay? And so at some point, Project Independence, that's not really true. Nixon didn't put solar power in Project Independence because it was believed to be outrageous in the early 70s that you could ever have solar power for civilian use. And then little by little, look at where we got. And now solar is one of the cheapest forms of power. So I've been lucky that I worked with Rick Smalley for the first years of my career before he passed away. And he has started the first company that commercialized carbon nanotubes. And so I know what it cost at the beginning to make nanotubes. And then after he passed away, I actually managed the facility here at Rice. And so this is where we started. And then this went off to two different companies, one in Houston and the other one in Japan. And then it went to another company, it's Coxill. And this is the values at which the nanotubes are sold. So right now, some of these materials that used to be essentially $1 million a kilo are down to $2,000 a kilo. Now, some of these companies are small companies. And so they had to put out a lot of press. And Preeti said, I spent a year at Shell nominally advising, in reality learning. If I see a press release that has the size, the capacity of a plant, and the amount of investment, I can work out now something that I used to be able as an undergrad chemical engineer to do, which is the capex incidence per unit cost of material, but I have forgotten as a researcher in nanotechnology, and I relearned when I was at Shell. So you can actually calculate what their cost is, and their cost is about an order of magnitude lower. So there are companies that are already making this type of materials at essentially a couple of $100 a ton. So the couple $100 a kilo. So these are still high numbers, okay? So these are like high carbon fibers. And so the next target is how do we keep this curve coming down? How can we push? We need to push like crazy to get the cost down. Now, normally, how does cost come down? Well, people say cost comes down with time, right? So these are remember, cost is measured in energy better than dollars. This is the energy intensity of making pig iron. So you take iron oxide and you make iron. And this is for the smelting of aluminum from aluminum oxide to aluminum. Now, it looks like it's coming down with time, but it's coming down with the total amount produced. Because if you don't produce, the efficiency don't go up, and energy intensity don't come down, and this is in log scale. Okay, so what it means is that achieving efficiency is extremely energy intensive. So programs like ARPA-E at the Department of Energy have actually been put in place to figure out how to go on different learning curves. So which means can you go on a steeper cost reduction curves by using science. And so because I don't have enough money to start building giant plants to make nanotubes and work out the cost reduction that way, I'm doing what I can with anybody who is willing to help to do cost reduction doing science. So how does this work? Well, it turns out if you look at how carbon nanotubes are made, there's about any source of carbon has been tried, including carbon dioxide actually, not only carbon monoxide. It's a catalytic process. You do need catalysts. Typically, we use iron. You need the carrier gas to bring catalyst in the system and keep the solids dilute. Reaction temperatures, they're moderate compared to what you see in metallurgy, for example. Lots of different reactor configurations. And so what we realized is that floating catalyst is the one that has the most scalable route because it leads to tubular continuous flow reactors, which are reactors that are used in a lot of chemical processes. And so now we're working on understanding all these steps, how the catalyst decomposes, the precursor of the catalyst decomposes, catalyst forms, the hydrocarbons decompose and lead to CNT nucleation and growth, and then the activation. What's important is not just these chemical steps, is the transport in these reactors. These are now real reactors. They are a few inches wide, meter to 2 meters long. There's a lot of transport, heat transfer, fluid mechanics going on, and so it's also important to control and understand that. So this is one of the reactors in our lab. So we're watching into the reactor. The reaction is starting, and what you see is the carbon nanotubes are getting formed, and they make something like a black smoke. The students call it the sock. And this is getting carried by the gas flow to the end of the reactor, and it can get collected. And we ran continuously for about an hour, and then we stop because it doesn't make sense for going longer. But companies like the ones I was mentioning are right now running for days to weeks continuous flow. So how do we understand efficiency in a situation where we have a reactor like this, where we put in methane, hydrogen, and an inert, and then we have a reactor with an electric heater, and that's where we have lab data. Okay, we started off with Aspen, and we made a mess, and so we did what's called the Fermi analysis. You do everything by pencil and paper, and you try to get an estimate like Enrico Fermi used to do, and then you go back to the computers. So this is what we have in the lab. Of course, this is a terribly inefficient reactor because anything that comes out of the reactor is vented out, right? So it actually goes to a burn box. In a real plant, it will look something like this. You would have a separator to pull out the nanotubes. You'll have an oxidizer to remove the unwanted carbon. You will remove a little bit of hydrogen so that the hydrogen doesn't accumulate in the system, and you send it back at some sort of temperature where you can recover heat, and then you would have some methane come in to balance the feed. Okay? And then it turns out that if you make it this simple, you can do everything by hand with what you learn in 301 here. Okay? It is great. Okay, so you can get a formula for everything, and you can actually get an analytical formula for efficiently. See, that my collaborator at the Carbon Hub, Marie Contucarrere, forbid me from putting on because it was a big formula, but it's an analytical formula. It's very nice. So you can actually get the efficiency of a process that would have the proper separations, heat recovery, and recirculations as a function of your reactor data. And so it turns out that when we were started, we were somewhere over here in terms of energy needed to make a kilo of nanotubes. ARPA-E gave us a first goal over here and a second goal over here. And between us and our collaborators at the Korean Institute of Science and Technology, we've been able to move down this curve. Sometimes it's actually back and forth because we're still trying to understand why some things work better than others. But we went up almost to orders of magnitude in efficiency. Huntsman is also in the same ARPA-E program, and they've been able to get amazing efficiencies, although they had to go down on the quality of materials. Now, the commercial manufacturers are actually at this level of theoretical efficiency, but in reality, they don't have heat integration and recirculation yet, so their actual efficiency is lower because the plants are still too small to put in the proper heat integration, etc. So to give you an idea where this is now in the same range of energy needed to make carbon fibers, okay? And not that far from aluminum. If we could get here where the goal that we set for ourselves, we would be competitive with automotive steel. So it seems that this is, I'm talking about something almost impossible, right? These materials were only used for aerospace until a few years ago. I'm actually increasingly convinced that we're not that far away from making these materials efficiency. Now, at any time you can hit the floor, okay? So, which is also what happened with solar. People never thought that they could keep going down. But if you don't try, this is worth trying, okay? So there is another part of the problem, which is not just making the powder. You got to convert the powder into articles. This is actually what most of my research was until a few years ago. I continue this research too. And we develop solution processing. So take carbon nanotubes and acids, put them together, and it turns out that the nanotubes love acids as solvents, and so they dissolve, they form liquid crystals, and then the liquid crystals can be extruded very much like Kevlar and other polymeric fibers are made, or our carbon fibers, and the extruded fiber is then coagulated in a bath and turned into solids. These can be extended to make three-dimensional foams, to make coatings, films, etc. We understand what drives properties. In polymers, what drives properties is molecular weight. If you want to have strong polymers or high-performance polymers, you need high molecular weight. Here, you need long-length nanotubes, so high aspect ratio of the nanotubes. And so that's how, for the last 20 years, we climbed up that property slope by making and using longer and longer nanotubes. And that means not only us, but we put pressure on the supply chain. You know, when we started publishing certain papers showing that longer nanotubes got better properties, lots of other groups and some companies started pushing to make nanotubes that were longer. On fiber spinning, we were working on process intensification. So we were getting great properties, but the problem was we had a pretty bad process. We were spinning at about 1% concentration, so 99% was moving solvents. And as a coagulant, we were using acetone, which is not good, you know, high CO2 footprint, high cost solvent. And we were collecting very slowly. A meter a minute is really slow for fiber spinning. We then introduced GS spinning, and I'll explain in a second what it is. In GS spinning, we could collect much faster. So now this is the range at which carbon fibers are made. We use water for coagulant, and we've been going up in concentration up to 10%. Why do we call it GS spinning? Oh, and we got the same properties. So you know, we don't have to sacrifice properties when we do this. So you see at top is conventional spinning. This roll is actually moving. You don't see it very well. And this is GS spinning. So a way to look at this process is on a map where you have properties like conductivity and strength, and then you have parameters that have to do with throughput, like concentration, cost reduction, and per hole throughput. So with a conventional process, we were trying to go up in concentration, and so drive up throughput and cost reduction, but we were losing properties very quickly. And so the reason we call just spinning is that when we made certain changes to the process, we were able to hit all the parameters that we wanted to hit without losing anything. And so with somebody to say you hit a home run, this is a home run with bases loaded, right? So we call it Grand Slam spinning. And we did this during the World Series last year. We did it, Oliver, one of my students. And so even at 10%, we have to give up a little bit of throughput and a little bit of strength, but it looks like we can actually do this at very high concentration. So we're no longer pushing properties, we're pushing process efficiency. The way I joke is I used to try to build Ferraris, and now I want to build a Model T. Okay? You can do a lot of cool stuff with these things. You have a very flexible material, it's carbon. It goes through sewing machines. So for example, here I have a sample. This is it can take your halter. So you put it on and you hook it up to an EKG reader, and it will take your halter, and it's much more comfortable to wear than electrodes. But there is also what happens is, this is an example, is if you want to use the material properly, you have to redesign the device. This doesn't look like any, if you have taken an halter in the doctor's office, that doesn't look anything like a halter you take in a doctor's office. And so this is something, a little problem. For example, you see it in bridge building. So that's a Roman bridge from Rimini, the Adriatic coast of Italy. Romans built bridges in compression because they had stone. And so when you build a bridge in compression, what's your material properties? It compresses strength divided by density. So Istrian stone is what the Romans used. It's actually better than steel. There's another thing, which is if you build a bridge like that, you got to be able to cut the material in place. You can cut stone. The Romans had no way to cut steel in place. So if somebody had cheap steel and gave it to a Roman bridge builder 2,000 years ago, the bridge builder would have said, don't want it. So you have to come up with a completely different design, right? So you have to have a suspension bridge where you use the fact that steel is very strong in tension, and then you can build, large span bridges. By the way, you got to figure out how to lay those cables, which is very different from the way you make scaffolds for bridges. So how do you start pushing this out, right? Not just making these materials more efficient and more inexpensive, but have people start adopting it. And that's why we started an institute called the Carbon Hub. And so it's designed to accelerate the emergence of an industry and markets based on carbon that actually has a value. And it's really as a consortium that funds the research. And it has an institute which is saying this field exists, pay attention to this, work on it, it's exciting, it's small, but it's going to become big and it's going to bring a lot of value. And also, we're now trying to have an accelerator component where we take some of the companies that have been forming in this space and get them to collaborate with us and so that they can work, they can grow faster. It has 4 main components. Oh, there's a delay between the screens, sorry. It's a community building, it's a square, education, school. Research is the biggest component right now, and we're also trying to influence policy. And for this, we're working also with companies and government agencies. We're proud of what we do because everything we're trying to do hits on some of the sustainable development goals of the United Nations. And so we're trying to produce clean energy in forms of hydrogen, decarbonize manufacturing and construction, improve efficiency of energy use, and not make CO2 emissions. We now have a good number of companies that have joined. It was launched about 2 years ago. And it's built as an open collaborator model. It's housed at Rice, but it's not restricted to Rice, which means that if you want to participate and you want to bring in a collaborator from Berkeley or from Illinois or from Imperial College, we can send them money, which is something that universities don't like to do when they get money from industry, okay? But we're trying to do this for a common good. These are the timeline, and we got both lucky and unlucky. Our workshop was in February 2020, and so we were lucky that we could do it in person, and then it was really hard for the next year and a half. But we've been growing our membership, we've been getting visibility, and we've been also awarding.
Your microphone battery died.
See, we should have had a fuel cell. Of course, I could have caught on fire. Well, I could catch on fire with a battery too. This is how the Carbon Hub is structured. I don't run the Carbon Hub. Marie doesn't run the Carbon Hub. We operate it really, but the leadership is coming from industry at the level of a leadership board that looks at the strategic planning, and we have right now members from Saudi Aramco, SABIC, and Shell, and a technical council that looks at the research directions and research outcomes, where we have also members from Prysmian, Mitsubishi, and Huntsman. We right now have projects, in many places in the U.S. Of course, rice is the dominant place, but we also have collaborations in the UK, in Spain, Italy, and South Korea. So Mark Goulthorpe is doing some of the most exciting work. He's also funded by ARPA-E and started a company recently to push carbon as construction materials, and it's very inspiring to think about how we could use carbon to build houses again, like we did a long time ago, right? The old houses were made out of straw and wood, etc. But now that we know chemistry, which we didn't do at the beginning of the Industrial Revolution, we could actually do it in ways that give us materials that have much better properties. So, this is a talk also about students. I always say that one of the great things about being a professor and doing research, that even if your research doesn't go anywhere, you train graduate students and postdocs, and sometimes even undergrads. And so these are some of these are the students, my former students who are in various companies and academia. I don't do much of the work, although I did the model, the pencil and paper model for the efficiency of a reactor. But certainly they don't let me in the lab, so this is my group. Most of them are here. And these are the companies that fund us and our academic collaborators. And so thanks for your attention, and the Carbon Hub is open, and will you join us?
Thank you, Dr. Pasquali. I know we're already a little bit over, but we want to have some opportunity for questions, so if you have some in the room.
One of Rick Smalley's visions was that the carbon nanotubes may one day be able to transport electricity from the remote locations where we have photovoltaic fields and wind farms, and transport it through high voltage, high amperage electrical conductors cross country to the cities where it will be utilized. So what's the outlook of his vision coming true?
So the outlook is actually pretty good, but for a reason that he hadn't thought about. The overhead power lines, the cost of a conductor is only about 5% of the cost of laying the power lines. About half of the cost is making the supporting towers. And so the power lines are not made out of copper, because copper is too heavy and not strong enough. They're made of aluminum reinforced with stainless steel. And the stainless steel is there so you can pull on the line, because these are, their cables are too thin to have intrinsic bending stiffness. So you get stiffness by pulling, like you get in the strings of a guitar. if you use carbon nanotubes, even the current material, you can put the structure, the towers, a much farther distance. And so you can reduce the cost of building the line a lot, which means you can then put more conductors. So even though this is not a ballistic conductor, Rick thought that we would get a ballistic conductor. You don't get a ballistic conductor above tens of microns because there is scattering. I mean, we're not at zero temperature. So it turns out that single carbon nanotubes are ballistic conductors if they're below about 10 microns in length, and then afterwards they become normal conductors. But they're good enough to compete with aluminum and steel right now for power lines, and you would get this benefit of having lower construction costs.
One more.
So I'm going to get a hard question now.
No, it's actually, it's an easy question. So you mentioned policy. What are the key policy bottlenecks in areas that you think this faces?
So for one of the policy bottlenecks right now is if people are going to get paid to clean up CO2 and get penalized for taking fossil fuels out of the ground, which is something that's under discussion, maybe not so much in the US, these would actually, these type of policies will discourage these pathways. Because here you don't capture any CO2, right? Because you never made it, and also you're still using a fossil resource, and so if you get penalized for using a fossil resource, you would have a disadvantage. There's no type of credit for displacing CO2 intensive materials, for example. So if you displace aluminum with something that has lower CO2 intensity, you don't get any benefit. So you have to show economic value without the CO2 displacement.
So I think in the interest of time, we will pause questions for now, and I encourage y'all, we will have a reception after this, and hopefully Dr. Pasquali will stick around and you can ask him some more questions as we continue. Before we break for the reception, I think we wanted to present Dr. Pasquali with an award for his presentation today.
I didn't know that.
Do we have a house photographer
Well, we
here?
have a videographer.
Fantastic. How about right over here? And then Prachi will be on this side, and I will be on this side, and man of the hour. How about this? And
Very good.
Thanks. Cool. Thanks a lot.